Hello, I'm Mike Mallon, and today I will be explaining gravitational waves. So, in 1916, gravitational waves were predicted by good old Albert Einstein. What a guy. But what is a gravitational wave? Well, first I will explain gravity. So, first let's imagine space-time, which space-time is a fabric which it like covers the whole universe. So imagine like a sheet like this of fabric. And when you put mass on a fabric, it sort of bends the fabric around it. It affects the fabric. It'll make it like sort of curve in. So that means that mass affects space-time. It causes space-time to bend like this. So if this is our sheet and you put a mass on it, it'll bend like that, and it'll affect the area around it. Now, applying this to the real world, if I say put a mass like and send it off in this direction, so I put a mass right there, and I send off right there, it'll rotate around this object, a smaller mass, and it will affect this mass slightly, but not as much as this large mass will affect that. So it will just rotate around it, like how the moon orbits the Earth. So gravitational waves, it's like when you drop a pebble into the ocean, and then it sort of ripples away in waves. That ripple would be like a gravitational wave. So how is gravitational waves caused? Get out of here. So how would a gravitational wave be caused? Well, the one that was recently discovered was caused by two big old black holes being merged. So there are two black holes, and what a black hole is a really condensed particle. It's like a shit ton of mass in it, and it's all condensed into one singularity, and has a lot of gravity, and it appears black because the gravity is so intense that light can't escape it. It's not fast enough to escape the gravity of a black hole. So when these two black holes merged in 0.8 seconds, it became one big old black hole. And when it formed up with this big old black hole, it released a lot of energy. And what this energy did was form into a gravitational wave. Like that. So the gravitational wave would send out in all directions. So, like, how is this better than just a regular light wave? Well, a light wave, it distorts over time because there's like dust in space. So those dust particles will actually distort this light wave. So you can't actually communicate with light over that big of a distance. But with gravity, it's not affected by the space dust. It's not affected by that. So then it doesn't distort over time. So we could take accurate measurements from it from a very long distance. Next, I will talk about how this was detected. So the engineers at LIGO, I don't know what it stands for, but that's the laboratory, it's called LIGO. They made this contraption, and what it did was, right here, it shot a little laser beam of light, like that. And it would hit this mirror, which separated the two beams of light. So one of the beams would go this way, and one of them would go that way. And then they hit another mirror right here, and then they would go back in this direction, or back to this mirror. And then there was also another sensor right here. Now what happened when they came back to this mirror right here? Well, it was calculated so that, well, light travels in waves. It travels in things called photons, which are particles, and it also travels in waves. So what happened was when these light waves came back to this mirror right here, they were perfectly aligned. The waves were perfectly aligned so that when they collided with each other, they would cancel each other out, so then there would be nothing left. So the light waves, the split light wave, would just annihilate itself once it collided with this wave right here. So, say there was a disturbance in one of these. There was a disturbance, so say like something knocked it slightly that way. These lights these wouldn't align correctly. Maybe one would be like that, and another would look like that. So that they wouldn't be able to annihilate each other because the waves aren't perfectly aligned. So they would be received. One of the waves would be received by this sensor right here, right there. So that's how, I don't know if you heard, but the light wave, it was just moved by like a fraction of a subatomic particle. That's how small the gravitational wave affected this. But how would the gravitational wave affect this here contraption? Well, when gravity hits light, when it hits this light right here, it'll actually change the distance that it travels. So when the gravitational wave makes contact with this, it'll actually make it so that it travels a longer distance back to this mirror. That's kind of complicated to explain right now. I don't really have enough time to explain that. But it basically makes it a longer distance from here back to there. So what that will do is that'll make it so that these waves are misaligned. So then when they meet back at this mirror, they won't annihilate each other, and then they'll be received by this thing. And that's how they know that a gravitational wave hit it. But what if there was, say, someone bumped into the sensor or something? Wouldn't that make it so that it fucks up? That's why they made it so that there's actually two of these things, and they put them on opposite sides of the world. So there's two. There's one on one side of the world, like that. So say like this is north, and this is the south. So that's the complete opposite sides of the world. So once this thing received the same measurement at the exact same time, both of these received the same measurement at the exact same time. That's how they knew that it was a gravitational wave which hit this thing. And yeah, that's how that worked. That's all I would like to explain today. Thank you and have a great night.